Okay, friends, the key point of the HV sampling and the low voltage side composition scheme is the setting of the phase angle offset set. As the SVG can only get the voltage at the lower side, and the SVG can get the high voltage side through the current transformer. The high voltage side and the low voltage side, their difference is a constant value. For DYN11 transformer steps, the phase angle between the low voltage and the high voltage is 30 degrees. And we put the high voltage phase at 12 o'clock, the low voltage angle will be at 11 o'clock. So that the low voltage is 30 in advance of the high voltage phase. For DYN5 transformer, the low voltage angle stays at 5 o'clock. So the phase difference between them is 150 degrees. So this is the voltage degrees difference between them. So if we have the low voltage angle by the setting of phase offset, we will have the high voltage angle. So that we will calculate right about the active power and the reactive power. So let's go to the meter and let me show you how to calculate the phase. Okay, here as you can see, we made experimental awareness here. This is the transformer. This transformer is also a DYN transformer. The voltage supply goes into the primary side. It's in delta connection, and in the low voltage side, it's in star connection. It has neutral. And here we have the meter. The meter is in correctly connection, and this meter can see the zero correct active power and the reactive power. So this is its CT, and this is its voltage probe. Here you can see that the active power is around 6 kilowatt, and the reactive power is capacitive and is around 4 kilowatt. Okay. And here on SVT, we firstly set the phase offset, this phase offset. Set it to 0 and read the results of the screen. Here, as you can see, we have the results. We have the current at the high voltage side. It reads around 20 amps, and this data is equal to the meter tells, so the CT is correct sample, and the CT ratio is correctly settled. And here we have the total grid Q and the total grid P. Here we have the total grid Q, that is capacity 0.3 kilowatt, and the active power is around negative 75 kW. So this is the summation of the data. As well, you can see that the data of Q and P among phases, they are balanced. So this can tell the polarity of the CT is correct. So the only thing we need to do is to correct the phase, to set the phase. Okay, we remember the setting and we go to the whiteboard. On the whiteboard, on the data we read just now, the meter tells which is the zero value. It is 55 and the capacity 4. So the angle between P and Q, it's 31 degrees. And if we draw in a diagram, we make the P as X axis and the Q as Y axis. As you can see, the meter, the zero power is here. It's negative 31 degrees. So here the active power is positive, the reactive power is negative. So this is This is a real value, real error. And here the SVT, we have the negative 7 kW and the negative 0.2 kV. So here the degrees diagram is 2 degrees, and if we put it in this diagram, we have the angle of the SVT data that is minus 178 degrees. Here, the SVT tells the angle is here, which is not real fact. So you can see that the difference between the real one and the SVT tells is around 150 degrees. So that we just need to set the phase offset of 150 to move the SVT calculation results to the real one. So we add 150 degrees. The total number of the calculation is 200. This is a constant value, and this is the one period total. So the number here is 83. 83. 83. So we set the phase offset of 83. Okay, here we set the phase offset to 83. Yeah, and now you can see the result has changed. You can see that the active power and reactive power is similar to the meter tells, which is similar to the real fact. And only by now we can start the device for compensation. And only by now can this device working normally. Okay.